Dr. Sanjay is also the coordinator of this TW course. It gives me great privilege and honor to introduce Dr. Sanjay Kumar Singh. Dr. Sanjay is serving as an assistant professor, senior scale at Indian Institute of Science, Education and Research since 2015. Before his joining, Dr. Singh was awarded PhD from most prestigious Tata Institute of Fundamental Research, TIFR, in 2013. His areas of research are algebraic geometry, coding theory. After his doctoral, he visited Research Center Mathematics at Mexico as a research scientist. After that, he worked as an assistant professor at Institute of Mathematics, Polish Academy of Sciences, Warsaw, Poland, during 2013 to 15. He has supervised 2 doctoral scholars and 1 postdoctoral scholar. He has published more than 20 research papers in various prestigious international journals. He was awarded 1 DST SERB project and 8 junior research fellowship projects in collaboration with the scholars from various institutions in India and abroad. Also, he has organized national conference and workshops, annual foundation schools as a coordinator. Welcome you, sir. I request you, Dr. Singh, to start his valuable lecture. Dr. Singh, please. Sir.
Yeah. Thank you, Dr. Pandey, for a nice introduction. As per the plan, our plan is to cover the portion from group and symmetry. So let's start. Is my slide is visible to you? Hello?
Not yet, sir. Not yet. Right now it is.
It's coming. Okay. Is it okay with everyone?
Yes, it is fine.
Okay. So as our title says, group and symmetry. So I will start with the symmetry and give motivation, and then again I will discuss this symmetry, group and other thing in second part of our lecture series. So let us start understanding what is mean by symmetry without giving any mathematical definitions, and basically by pictures. So I think most of us have seen such type of pictures. So, and in this picture, I am defining something called line of symmetry. That is very important to say that object has a symmetrical pattern with respect to this line. Now let's move on some more example. This is also a symmetry. So for any question about the pictures and whatever I am saying, that symmetry is fine with everyone? Do you agree some symmetry is there? I will be happy if someone answer me in between. At least yes or no.
Yes, sir, it is fine.
Yes, so symmetry wise fine, but what is the mathematics? So far, whatever I'm saying, it is by picture, you can believe that, okay, this is a symmetry. Yes, here you also have a symmetry. Okay, let's go more example. Yes, what about in this picture? So of course, symmetry was based on the line of symmetry, and if I take a line of symmetry different, then even you get a symmetry of object, but with respect to other line of symmetry, you will not get. So like in picture 1 and 4, of course, everything is fine. But if you take a picture 2 and 3, then you can say, no, with respect to that line of symmetry, this object doesn't look like a symmetrical. Is it fine? So now I'm trying to move to define some mathematical definition of symmetry. Picture by picture, we are convinced and we are happy. Okay, this is a symmetrical object. It looks like this. But when I said line of symmetry, then it is telling you something more, and it is telling you something called a reflection. So line of symmetry plays a very important role, and now you are not thinking this object as just looking a nice object. You are thinking this as some transformation is happening on this object, and after the transformation you are getting again a same object. And what is the transformation in this case? In such examples, reflection. If you take this line, can you see my pen movement?
Yes, sir.
So if you take this line, about this line, if you reflect a point here, you will come here, reflect this point here, you will come here. And after doing all this transformation, so even you can define this transformation on whole plane, R2 to R2. And plane can be represented by R2. And you can define a map called reflection. And under this map, you can see the object is same. There is no difference in object. Even points are moving, but whole shape and size of the object is same, position is same, there is no change. But if you take this line, then it is not working. So it is giving you intuition how to define a symmetry in mathematics. So in geometry, an object has a symmetry if there is an operation or transformation such as translation, scaling, rotation, reflection, something like that, that maps the figure object onto itself. And if such thing happening, so we say, okay, in geometrically, mathematically, we have something called symmetry. So now symmetry is not just a picture for us, it is basically a transformation which help us to find the symmetry in the object. Now look some more example. So this is my picture is not good here. So this is an infinite strip, you can say, infinite, and the symbols are infinite. So this, so simple like this, continuous here and here. So what I'm doing, I'm again applying a transformation here. And what is my transformation? I'm moving a point here. Suppose I have a point here, I will move. Suppose this is my point. 1 minute. This is my point. I'm moving this by distance d. And again, I have some point here, then I'm moving by distance d. If so, such type of transformation are called as a translation map. So basically, I'm translating a point by a distance d, and if all object has a distance d, then you can easily see that after applying this transformation, there is no change in this picture because this is infinite. If it is a finite, then of course there will be change because last one will go to the next one, and which is not in this picture. So I have given you picture. Now picture we came to in mathematics, and then we have realized that symmetry are just like some transformation. And now we are trying to find out what are the nice transformation which gives again symmetrical picture which we have seen just by intuition. So now let us go to the another example. Can you see my example picture? So our foot is step. So suppose this is again infinite. From here there is no end. So again you believe that okay, it is a symmetry. But now we know it as a mathematically how to tell symmetry. And what is a mathematical thing? Okay, if I want to explain it mathematically, then I will say, okay, it is some type of special transformation which leaves object again same. And here such type of transformations are called glide reflection transformation. What is mean by glide reflection? Whenever you have an object, either you translate it, means you take this foot, translate it again here by distance d. Suppose, and also we are assuming the distance between each two foots are same. Here d, d. So either you translate it, you translate it here and then reflect it about this line. Or you just reflect it here and then translate it. So reflection and translation together is giving you some different type of transformation that is called a glide transformation, and this also give you different type of symmetry that is called as a glide reflection symmetry. So now more example. So let us take a triangle, and now again I am talking about what are the possible symmetry, what are the possible transformation in this plane such that this object is going to the exactly same. There is no change in this object after applying the transformation. So another example is that if I rotate our plane by 120 degree, then what will happen to this triangle? After rotating, this red point will go to here, blue vertex will come here, and green vertex will come here. So position of all three vertex will change, but still whatever object you get, there is no change in the object, both are same. But there is some transformation which giving you a nice leaving the space same. There is no change in the space of shape and size of the object. And such type of transformation we have also seen that they are called as a rotation transformation. And so they are also giving you some type of geometry, and that is, you can say, rotational geometry. So mathematically, I think I have given enough example to you about the symmetry. Now it will be very interesting question to know what are the all possible symmetry, at least inside the plane. Again, we can go in higher dimension, but first we restrict ourselves in a plane and ask the same question. So this answer we will give again in the second part of the question, lecture series, maybe a different week. But before that, I want to stress on the fact that if I consider all set of all possible symmetries of triangle, like in this picture, I have given you many symmetry. Like I can take triangle, I can take line of symmetry, and then I can reflect it. This point I can send here, and after reflection, I will get the same object. Similarly, I can take line of symmetry like this, and again reflect it, and I will get the same object. And here you have a different. So I have given you different transformation, and which I am expecting to call symmetry of that object. And interesting point is that this set is very interesting for us. Why? Because this set has some algebraic property. Of course, objects are coming from geometry, but this shares some algebraic property. And what is the property? Just look. Let us step back a minute and consider what are the algebraic structure these examples give us. Of course, if you consider the set of symmetries, then they have an operation. What operation? Means if I give you two symmetries, then you can produce the third one. What is this? Like this, see here. I can rotate this triangle 90 degree, and after rotating, I can take reflection. If I compose them as a map, I can do always, and after composition, you will again get a transformation. So it means this set tells you that this set of symmetries has a rule. Whenever I take a two element, then I can give you another element in this set. And similarly, it has a more nice property like that. If you do a transformation, A and do B and C together, then it is also same as the doing a transformation AB together, and after that applying C. Of course, there is another transformation, something called identity map here. And what it does nothing. Symmetry does, it is a symmetry which does nothing. And also this symmetry has a property that if I compose this symmetry with another transformation or symmetry, then I will get the same I will get the same symmetry. So it is not doing anything if it applies to the another symmetry. So something is like identity. It is leaving everything same. There is no change after multiplying with this element. And finally, also, if you see, whenever I give you a symmetry like here, suppose I say I'm rotating this as a 90-degree and I get this, then I can also rotate back and I can come back to the same position. And that is giving you something called, okay, there exists some type of inverse of each transformation. If I'm rotating by alpha degree, then clockwise, then I can rotate it anti-clockwise alpha degree, and I will get the same transformation, whatever I start identity. So this set is motivating us to understand some set, motivates us to consider some set with some nice property, and that we are going to call group. And to define mathematically, let us start with systematically. I will define what is called a binary operation on a set. And what is a binary operation? Like in symmetry, whenever you have a two symmetry, you can give me third one. So this binary operation is like that, but mathematically, I will define them as a map. So let S be a set. A binary operation on S is just a map mu S cross S to S. And for example, you take a S is equal to Z, then I can define a map which is sending xy to x plus y minus x dot y, where x plus is a usual addition of two numbers and dot is a multiplication of two numbers, and minus is a subtraction of two integers. Then of course it is a well-defined map, and by definition this is my binary operation. And now I'm looking some nice property about this binary operation. So before that, I will fix my notation in this lecture series. Sometimes I will denote the symbol mu xy with this, just xy or x circle y or x dot y or x plus y or x star y. So whenever I write like this, it is clear that it is the image of the map, which is mu of the point x comma. In simple sense, again by picture, I can say that the binary operation is nothing but it is just like a machine. And what machine does? It takes 2 points x and y and produce another point. So far, any question?
No, sir.
No, good, thanks. So now, after binary operation, I'm ready to define some nice structure on a set with a binary operation, and that is, you already guessed that is group. And what is a group? Group is just a set with a binary operation mu, and always I will not write mu. So binary means mu from G cross G to G, a map. Whenever I take two element, I can talk about the third. With that, if this set has this binary operation has three properties. First is called associativity. If I multiply G and H and then multiply with K, so basically it is a mu G H K. And what is GH again? GH is by definition mu of GH, and again I'm gonna write this. So this operation is same as multiplying G with G, and first you multiply H and K and then multiply G with H. And similarly, it is asking you the existence of some identity element, which you can also write a neutral element. It means there exists a point E in G such that EG is equals to GE is equals to G for every G in capital G. And third, it is demanding that whenever you have an element G in capital G, then there exists an element H in capital G such that GH is equals to HG is equal to E. In my example, whenever you rotate 90 degree, then you can again rotate back in different direction 90 degree, and you can achieve this element H for any G. So now again fix some notations. The number of element the number of element of a group is called the order of the group, and we denote it by just mod of G. A group G is called commutative if for every G and H, this operation mu GH is equals to HG. And if operation is commutative, then we denote this group by abelian. So we say the group is abelian group if the binary operation is commutative. Any question?
No, sir.
No. So now let us see examples. So now this Q denotes the set of all rational numbers. Then Q star forms an abelian group with respect. Oh, sorry, there is some notation typo. So then Q forms an abelian group with respect to the usual addition, and the identity element of this is 0. And if you take a Q star, then it forms a group under multiplication of two numbers, and identity element is 1. So again, let R denote the real number, then R star forms an abelian group with respect to usual addition. I think some typos are there. Here I think I should write multiplication. Multiplication. And similarly, if you take a Z set of all, this is also a abelian group. Here star is not there. So Z with the set of integers, then Z forms a abelian group with respect to usual addition. And then identity element is 0. If you take n set of the all negative integers, then you can easily check that it is not a group. Why? Because if I take element 1, then there is no element A such that 1A is equals to 0. So it is not a group, because with respect to, of course, you can make it as a group, but with respect to usual addition, it is not a group. So more examples are Q star, R star, C star, Z star. But again, Z star is not a group because it doesn't have a inverse of the element 5. If it has an element inverse of the element 5, then it demands that phi of x is equals to 1. It means x should be 1 by 5, which is not possible because it is not an integer. Now, some new examples. Like R star, there is something called GLNR, which is a set of all invertible matrices, n cross n invertible matrices, and we can see that actually this is a group with respect to usual multiplication of matrices, and you can also verify that it is not an abelian group because you can always find example of matrices such that AB is not equals to B. Now some more example. Zn, which is a just, and I am defining what is mean by Zn. It is a just set of element 0, 1, 2, 2 and minus 1. And on this set, I am defining operation such that if you have a AB in Z, then A plus B is by definition is C, and AB is equal to D, where C and D are the element in Zn, such that A plus B minus C and AB minus D belongs in NZ. Means A plus B minus C is divisible by N, and AB minus D is divisible by N. Then it is easy exercise to check that. On this set, I have defined some operation, and with respect to this operation, this set forms a group. Similarly, I can define a new set called UN, which is a set of all elements A in Zn, such that An is 1. What is mean by this notation? This means that GCD of A and N is 1. Then you collect all this set element and call this set as a UN. And I can define an operation which is basically a multiplication operation, A, B, which is just D, where A, B minus D is divisible by belongs in and defined level. With respect to that multiplication operation, we can verify that actually this set is a group. But this set is not a group. Zn with respect to multiplication is not a group. Sometimes we use some table. Basically, to want to tell binary operation, what you need. You want to tell whenever you have a two element x and y, you want to tell what is their product. So we sometimes use a table when group has a finite order and very few elements, and which is not very big, it means like a small order. Then we represent it by a table, and what we do, we write here multiplication. Here we write elements x1, x2, xn. Again here write element x1, x2, xn, and then in these tables we write them what is the product. What is after applying boundary operation, what is the value? And again, this representation is useful to detect that what type of binary operations give you a group structure, but it only works on the set which has a cardinality very small, very low degree sets. So now come back to this is actually called as a Kelly table. We call such type of table as a Kelly table, and in this example I have made a Kelly table for Z4 with respect to operation addition and with respect to multiplication. So you can see if you take a 0 and 0, then what is the sum of 0 plus 0? That is 0. If you take a 0 and 1, then what is the sum of 0, 1? That is 1. And if you take a 0 and 3, then what is the sum? This is 3. If you take a 2 and 2, then what is the sum? 2 plus 2 is 4, but 4 minus 0 is belong in 4z, so it is a 0 by definition. And again, with respect to multiplication, I have made. So one interesting question I said, is it a group? So how will you check it is a group? So to check group, you have to make sure that this is always same as this. If this is identity, then this row is same as the first row. If this is identity, then this row column should be same as this one. But this is not a case, so 0 is not identity. If you consider, okay, 1 can be identity, so you can check this one case, this is fine. And this is also fine. But here you can see that this element has no inverse, this element has no inverse, this element has no, you can find many elements which has no inverse. So that's why this operation is not good on Z2, but it is good on U10 here. But again, if you consider plus operation on U10, then it is not actually a binary operation on U10, because if you add two numbers, then you can get some more numbers which are not on this set. So like 6 is not in this set. So with respect to plus, you cannot even get a binary operation on this set. Similarly, we can take any element of set of element 4 and we can form the Kelly table and we can deduce many things. So one exercise is that so that there exists no other binary operation on S which makes X to be a group other than these two multiplication tables. Means you cannot find another multiplication table on a set of 4 elements which gives you a group structure. Yes. So any question?
No, sir.
Good. I assume that many of you have such things. So you are
Hello, sir. The example of group, example number 11.
Yes. Yes. Hello. So it is a group with respect to addition only. And with respect to multiplication, it will be group only if n is a prime number. And here I have taken example. If z is equal to 4, then it means it is not a prime number. And with respect to this is not a, this multiplicative table, a Cayley table is not giving you a group structure with respect to multiplication. Hello? I think we lost. Okay, so now some more notation. I said the number of element is called the basically order of the number of elements of a group is called the order of the group, and I will denote with these symbols. And whenever group has an infinite number of elements, then I will denote it by mod g is equal to infinity. It means group has an infinite number of elements. Now in a group, I can define a notation, this what is called a power n. It means you take one element and it's take image. Basically, you consider what is a square, which is a dot a. If you want to consider a cube, then it is a dot a dot a. And similarly, you can define the n time product of any element, and I will denote this by a power n. If n is negative, then basically I will take a n times inverse. And since you are working in a group, then you don't need to worry about the inverse because it automatically exists by the property of group. And sometimes I will denote them as a plus L, a if my operation is a additive operation. So these are the notation I am going to follow. So for example, if you take a g is equal to z, then 2 power 3 means what? With respect to operation in g, I will add or multiply 2 3 times. And since operation is plus, so I am writing this as a plus, and it means 2 plus 2 plus 2, which is 6. And similarly, you can calculate others. For example, here, if on z, I can also define operation like that. And with respect to that operation, what is the value of this? It means I am adding or multiplying 2 3 times. So how to do this? Because I know value of only 2, so first I will multiply 2 and 2, and by rule it is a plus b plus a dot b, which is this. Now you got 2 multiplied with 8 with respect to this formula, and again apply this formula, you get a 2 plus 8 plus 2 dot 8, and that is 26. And similarly, other exercises you can do. So now some more definitions which I need. I am going to define what is called as a order of an element. An order of an element G in a group G is actually a smallest n. Yes. The order of an element, can you see my mouse movement? Hello?
Yes, sir. Yes, sir.
Yes, good. So the order of an element G in a group G, capital G, is the smallest integer n, such that G power n is equal to identity. If no such G exists, no such n exists, then we say that G has an infinite. And sometimes we use the notation this, or mod G or order G. So for example, if you take a 2 in Z4, then 2 plus 2 is 4, and 4 is 0 in Z4. So order of this is 2, means 2 power is equal to 0, and which is identity in Z4 with respect to addition. So order is 2. And if you take a G3, then with respect to addition, order is 4. And if you take any element in Z, then you cannot get a 0 element after taking finite powers. So any element in Z has a infinite. And we have very nice propositions about the power of the element, which is very easy. Why? Because if you want to write Yes, if you want to write a power m this, so better you write a power m times, and then you write a n times, and then again you get a power m plus. And similarly, you can do other exercises, other steps, other part of the proposition. And now come to the another example, that is called symmetry group of finite set. So I want to define what is mean by symmetry group of a finite set. So let X be a finite set and denote the set as X. So this set is basically a all bijective map from X to X. So what I said in beginning, what is a symmetry? Symmetry means some transformation such that after doing this transformation on a set, you will get exactly the same set. So if I take a finite point, if I take any bijective map from this finite point to finite point, then this set will be preserved because it is a bijective map. So n point will go to n different point, but set wise it is same. So on this set, we can define an operation, which is basically composition of two maps. And this operation is sending a sigma and tau to the tau composed with sigma, or some people define just like a sigma composed with tau. So on this set, you have at least two way of defining a binary operation, and they comes very naturally, just a composition of map. And with respect to this binary operation, it is very easy to check that this group is this set, and this operation is giving you all properties of group, and hence we get this set is a group with respect to this composition, and we call them as a symmetry group of X. So now the definition of symmetry group of X is very clear. Generally in practice, we don't use any X. We put a particular X, 1, 2, and n. And with respect to this, the symmetry group Sx is denoted by Sn or Pn, depending on books. And they are basically what? They permute these numbers 1, 2, and n, and hence we call them as a permutations. So these maps from 1 to n to 1 to n is just permuting these numbers, and we call them actually a permutation group. It is very interesting to check that order of this group is actually a factorial, and so basically you have a question that you have a set with an element, kernelity of set is n. So what are the map from S to S, which are bijective maps? So this number is actually a factorial, and now some notations. We will use this, we call them as an array form. How this array form of a permutation is represented. So basically a permutation is a map. So whenever you have element 1, so now suppose A1 is the image of this 1, so I will represent like this: 2, A2, and AN, where AI is nothing but the image of I under the map. So this form is called as an array form. And for identity map, I will use either I or this. This is a symbol notation. And again, since we have observed that here we can define at least two ways. So in my lecture series, I will fix one way, and this way is like this. So product I will define like this. So whenever you have a sigma and tau in Sn, then I will define the product of two permutation like this. And you can again some more notation for what is mean by cyclic permutation and cycle representation of a permutation. So an element sigma in Sn is called R cycle if there exists R symbol I1, I2, IR, such that sigma of I1 is equal to I2, sigma of I2 is equal to I3, and sigma of IR is equal to I1. It's like a cycle. I1 is going to I2, I2 is going to I3, and similarly like that. And how to represent them as an array form? It's like this. I1 is going to I2, I2 is going to I3, IR is going to I1, and other symbols are fixed. Rest are fixed, so IR plus 1 is going to IR plus 1, IN is going to. It is also interesting exercise that if you take any cycle of length R, then its order is also R. So examples, S2 is a permutations of symbol 1 and 2. So all maps from 1 to 1 to bijective maps, and they are represented like this. Similarly, I can define S3 and more thing, some more remark. I can consider any permutation group Xk inside the S. And how we can do this? Because suppose I have a map from the set of kernel Tk, bijective map on the set on kernel Tk. I want to produce a map, a bijective map on a set of kernel Tn. So how can I do? I can fix k element. I can define their image. I can take k element and define their image by using the element in Sk. And rest we can just define identity map. Each element is going to same element, and thus I can always produce sigma n using a sigma in Sk. So some more notation, cycle to some more conversion. Yes. So how to represent cycle from cycle to array notation? How to come from cycle notation to array notation? So it is like that. In cycle notation, you know 2 is going to 3, 3 is going to 4, and 4 is going to 2. So what happened to 1? So it means 1 is going to 1. So I have represented like this. 1 is going to 1, 2 is going to 3, 3 is going to 4, 4 is going to 2, and what about 5? 5 is fixed. So this is a cycle to array. Array to cycle. Now let's see how array to cycle we can come. So like here, now I have an array, I want to produce a cycle notation. So what I will do, I will start from here. 1 is going to 4. What about 4? 4 is going to 10. What about 10? 10 is going to 1. So this cycle is closed. Now I will take a 2. So 2 is going to 3, 3 is going to 9, and 9 is going to 8, 8 is going to 7, 7 is going to 2, and 2 is again going to 3. So now 7 is going to 2, so it's closed. So now you have seen that how to go from array representation to cycle representation of any permutation. 5, 6 are missing. So what about the 5, 6? So 5 is going to 6 and 6 is going to 5. So it means this is. So I got a. And now I will define how to compute the product of 2 cycle. So suppose I want to compute the product of 2 cycle. So what will I do? I will first make 1, 2, 3, 4, 5. And now I will look what are the image of these under this product permutation, under this permutation, which is a product of cycle. So how to do this? 1 is going to 5. So I will draw like this. 1 is going to 5. And now 5 is, so now it's done here. Now what is happening here? 5 is going to 5 under this. So this 5 is going to 5. And in this cycle, 5 is going to 3. So I go like this. Similarly, I will do with 5. 5 is going to 3. And here 3 is going to 3. And here 3 is going to 5. So this. So after doing this, I can always get this. 1 is going to 3, 2 is going to 4, 3 is going to 2, 4 is going to 1, and 5 is going to 5. And then again, this is actually array form. So it is written like this. And this array form you can again convert it to cycle form, and it will be like 1 is going to 3, 3 is going to 2, 2 is going to 4, and again 4 is going to 1, so closed, and 5 is going to. Or we also write like this because singleton element we just assume that it is fixed, so we sometimes write and sometimes we don't write. Again, if I change my rule, then I have given exercise again how to get this product, which is very easy, and you can check this. But interesting thing is that if you change a rule, so this is a rule. Before that, I have taken this rule, which we are going to follow in whole lecture series. But if you change the rule, then this product is not same. So it is very important that when you start, then you fix one rule and follow our calculation based on that. So for any question?
Sir, while we compute the product of cycles,
Yes.
We need to start from the left side towards right side, sir. Or
no, that's why I said no. There is a two possibility. Either you start from left to right, or you start from right to left. So I have in my lecture series, I am fixing left to right. But that's why I have given you a calculation. Here, this calculation is different. You check carefully. Okay. This is a right to left calculation. And I told you that if you do calculation, then you will get a different answer.
Okay. Thank you.
So now you have solved my problem by asking this question. So if you want same answer from me and your answer also compare, then you follow one rule. And for this lecture series, we are following this rule.
Okay, sir. Thank you.
This is a rule. Where is this? Yes, this is a rule. Okay. This is a rule for us. Okay. So this rule comes basically the composition of matter. Okay. So now we just move. So now what we have done, just recall again. We started with some nice set, and that set came from geometry. And on this set we have observed something, and what we observed is some nice properties. Because this set has a nice property, then I thought, okay, why to study this set? Just study any set with such nice property which we have already realized. And then we realized that this set, we have defined that set as a group. Now we want to move and study this object. So before going this, I just want to tell you how the mathematics is developed. Most of the mathematics, if you see in future, is developed like that. So there is something called group theory. There is something called topological theory, topological spaces, something called manifold theory, something called algebraic geometry, something called complex geometry. So what are the building of this all mathematics? Building is that first is important, what are the objects we study in such type of mathematics. So like in group theory, you study groups. In topological spaces, you study topological space, that is object. In manifold theory, you study manifold, that is object, and go on. After doing this, defining this object, the next goal is to understand this object. And how to, so if I give you two objects, can you tell how they differ? So if you want some difference in this, then you create some property. So like in my lecture, if I want to check how two participants are different, then I will create some examples or some questions and I will ask them. And I will characterize them like that. Okay, someone is giving all answer, it means he is brilliant. Someone he is not giving any answer, it means he is super brilliant, like that. And then it will be easy for me to divide my class and distinguish between two objects. The same question I am asking in group theory. How can you distinguish two groups? Even on the set of 4 elements, you have a 2 different group structure, and how will you distinguish? So this is a fundamental question which we will answer, and still the answer is open in general, and people are giving different way to understand this question. Okay? So when you have an object, then how to study? So now go back to the sets. And in sets, what you have done? Whenever you study a set, you study a subset. You study what is a union of a set. You study what is a intersection of a set. You study what is the difference of a set. So here also we want to say, okay, since we are working on a set and we are defining some nice structure on this set, then what can we say about the subsets of this set? What can we say about the union of two subsets? Something like that. But you know, we are interested in set with nice property. So we are not interested in just only a subset. We are interested on some subset which has some nice property, and such type of object I'm going to define as a subgroup of a group. So let us define. So subset of a group, which I will go to call subgroup. So what is a subgroup? So subgroup, so let us start. Let G be a group and H be a non-empty subset of G. We say H is a subgroup of G if H is a group with respect to the binary operation coming from G, and we denote by this symbol. This is the symbol. Whenever I write like this, it means I am saying that H is a subgroup of G. So it means it is a group in itself, but it is a subset of some bigger group. So I will call them, okay, subgroup. Okay. So example are like that. Of course, in a tutorial you can discuss more example. So if you take a group of integers, and if I consider a subset mk, where k is varying over all integers, then this set is represented by mz, and of course it is a subset of z plus. But we can, if I study this operation on this set, so with respect to this operation, this set is rich and it is actually a group, and hence it is a by definition subgroup of Z. Similarly, if you take a Q plus, which is a group of all rational numbers, then set of integers is a subset of this, and with respect to this operation, if I restrict it here, then this forms a group. And since it is a subset of this, so we call this as a subgroup. And very simple example of subgroup is a H is equal to identity. So this is actually called as a trivial subgroup of G. So again, question is that, okay, now we know a subgroup of a group. So if I give you a subset, how to tell that it is a subgroup? Of course, I can check all group property and tell, okay, it is a subgroup. But can we minimize my operations? So yes, this proposition helps you to minimize your operation. It says that if G is a group and H be a non-empty subset of G, then H is a subgroup of G if and only if A, B inverse belong in H for every A, B in H. And in addition notation, you can just say that A minus B belongs in H whenever A, B belongs in H. So proof is very simple. Basically, you want to show that if such thing is happening, then H is a group. And if H is a subgroup, then it is always true. So let us prove. So suppose that H is a non-empty subset of G with the property that AB inverse belong in H whenever A and B belong in H. To show that H is a subgroup of G, we must prove that H satisfies the axioms of a group where the operation is multiplicative of G, suitably restricted to H. So I will check that H has identity. So let us see. Since since H is non-empty, sorry, one notation is missing here. So since H is non-empty, there exists A in H. Since A is there, so I can take A comma A 2 times, and by property AB inverse in H, so A inverse in H. But what is A inverse? Inside G, it is identity, so E is also in H, which is identity of G. And also it is very easy to observe that HE is equals to HEH. Why? Because this operation holds in a group G, and that's why it holds in H. And thus you found a identity element inside the H. And similarly, for any A in H, you can talk about EA inverse, which is basically A inverse, and which is also element in H. So A inverse is the inverse of A inside G, but it also works as an inverse of A inside H. And similarly, you can prove the closure property. There are some nice examples of the sets, subgroups. We define, suppose G be a group and A be a non-empty subset of G, then we define something called CGA, which is all G in G such that GAG inverse is equal to A. This is called a centralizer of a set A inside G. Similarly, we define a center of a group which is all element in G such that Gx is equal to Xg for all G in capital G. Means all elements which commutes with other element in G, all element in G. And also we define something called some subset NGA, which is called as a normalizer of A in G, which is all G in G such that after applying G inverse on the set, we get a set. So we can check in tutorial if there is any doubt. And these are actually not just only subset. These two forms a subgroup of G. Now we have some new special type of normal subgroup, a special type of subgroup which I call as a normal subgroup. I will tell you why this group is important, why this subgroup is important later in my second lecture. But so far I am defining a nice subgroup that is called a normal subgroup. I will say a subgroup H of a group G is called a normal subgroup if for every G in H and for every H in capital H, G at G inverse belongs in capital H. And you can see actually any subgroup of an abelian group is always a normal subgroup. And also you can check that if I take a subgroup H, which is just here 1, 2, 3 means identity. So this notation is not good, but yeah, some problems. Okay, so I will just, this is a group generated by identity, an element which is sending 1 to 2, 2 to 3, and 3 to 1. This notation is different. So this notation is 1 is sending to 3, 2 is going to 1, and 3 is going to 2. So this set is also a normal subgroup of S3. Now I am going to define some nice groups that is called a cyclic group, and I will also talk about the subgroup generated by a subset of a group. So let G a big group and S be any subset of G. We say that S is a generating set of G if for every A in G, yes, for every A in G, there exists element G1, G2, Gn in S such that A is written as G1 power R1, G2 power R2, and Gn power R. So we say that the group is generated by this set where this all Gi belong in S. Similarly, example, you can see that if your set is S1 is 1 and group is Z, then all element of Z is generated by the set 1. Why? Because if you take any element n, then I can take 1 and add them n times, then I can get Z. And since S1 is generating G, then of course S2, we can similarly check S2, S3, and S4. So what about S2? Can I write 1 in terms of these two elements, power of these two elements? No. Because if I take any power of these two elements, then 2 will be common and that number will be divisible by 2, but 1 is not divisible by 2. So that is, this set S2 is not a generating set of the group G. remark, for any group we can always find a generating set, but it need not be. Of course, I can take whole group as a generating set. So finding generating set is not a big deal, but finding a generating set with minimal element is an important thing. And the cyclic groups comes in this picture. It is a group which is generated by just a single element. So if I have a group which has only one generator, then these groups are very nice and we call them as a cyclic. So for example, Z is a cyclic group which is generated by 1 and -1. Zn is isocyclic group which is generated by any A belonging Zn such that GCD of A and N is equal to 1. And similarly, I will define a subgroup generated by a subset, which is a definition. Definition says that let S be a subset of a group G, then the subgroup generated by S is the smallest subgroup of G containing every element of G. For example, if you take S is equal to M and N be a subset of Z plus, then the subgroup generated by this is basically KZ, where K is a GCD of M and the proposition, let S be a subset of G, then there exists, spelling mistake, yeah, then there exists a unique subgroup generated by S, and moreover, it is actually an intersection of all subgroups containing the elements of S. Also, any element of the subgroup can be expressed as the finite product of elements in S and their inverses. And we generally use this notation. So this notation means the smallest subgroup generated by S is for this. So like this, in example this. So this, what is the smallest subgroup generated by 2030? So this will be of the type this. All element of this form are in this set. And you can also check that actually it is a. So now what we have done already, we have started a group, we have understood a subset. Now question is that what about the map between two sets and what about the map between two groups? So now we are going to understand what are the nice map between two groups, and nice maps are like that. So let G1 and G2 be two groups and let phi G1 to G2 be a map. If this map has this property, you take two elements in G1, multiply them, you take two elements in G1, suppose G and H are two elements, multiply them, and what you do, you send their image phi G, here phi H, and take image here phi GH. So now your thing is that I can multiply them here because they are element in G2. Now I have another element here. So what about this? If such thing is happening, then we say that such maps are very nice because they preserve group operation, and these maps are basically called as a group homomorphism, and they are very interesting to study. And now we have some nice propositions. If you take any group homomorphism phi from G1 to G2, then phi is sending identity element of G1 to identity element of G2. If you have any element G in capital G1, then the inverse is going to exactly the inverse of its image. And if you have any element which has a finite order, then image also has a finite order. And more, the order of image element divides the order of G. So how much time I have?
So 10 minutes. 10 more minutes.
Well, yes, just I will quickly finish. It's
Yes,
done. It's just done. 1-2 minutes I will take. So just I want to again advertise that I have taken a set. I have defined a nice structure on this. Then I have looked at some nice subset. Now our aim was to understand the nice maps. And now I convinced you that because of operation, this is a natural way to understand the nice map. And what are the nice map? Which preserves the group operation. And these maps I'm going to call as a group homomorphism. And example, you can see that if I take R to R star, the map phi x is going to e power x, then you can see that R is actually a group with respect to addition, R star is a group with respect to multiplication, then this map is actually a group homomorphism. Why? Because if I take two element x and y, if I add them, then I will get x plus y. And what is the image under this map? It will be ex plus y. But if I take image of this, then it will be ex, image of y, it will be ey. And again, if I multiply them, then I will get a ex, ey, and which is same as this. So this is a nice way of just nice maps, and this satisfies the all property whichever I mentioned, group homomorphism property, that for any gh, phi of gh is equals to phi g, phi h. And hence, this map is an example of group homomorphism. And similarly, if you take a map phi from GLN R to R star, and what is the map? Basically, it is a determinant of the matrix. We know this determinant matrix has this nice property. Determinant of AB is same as determinant of A, determinant of V. And what is determinant of A? This is phi A and phi V. So this phi from GLN R to R star is actually a group homomorphism. So determinant maps are also very interesting and very important in group theory, and they provide you very nice map, and which is actually a group homomorphism. So now another remark is that there is no non-zero group homomorphism from Z2 to Z. Why? Because I just mentioned that if you have any map, then if G has a finite order, then image also has a finite order. And if you see what is the order of 1 inside Z2, it is finite, it is a 2. So if this element has order 2, then its image will have also order finite. And in Z there is no element of finite order, hence you will not get any non-zero group homomorphism from Z2 to Z, because one image of 1 forces to be 0 if your map is group homomorphism. And there are two nice sets corresponding to any group homomorphism. One is called a kernel, which is a collection of all G in G1 such that phi G is equal to E2. And image is a set of all element of the type phi G, which are the image of the element in G. And these two sets are very nice. Actually, they forms a group. And more, this kernel phi forms a normal subgroup, but image is not a normal subgroup. Why? Because you can take identity map from S2 to S3, S3 to S3, and image is non-abelian. Okay, sorry. So yes. So I can always take a non-abelian group, and its image is actually okay. Something I think I should not say anything here. This example is not good. Identity map is not good, but I can always find many examples where the image is non-abelian, not normal, but yes, group is this image is a subgroup. And again, last definition: a group homomorphism phi G1 to G2 is called an isomorphism if this phi is a homomorphism and phi is 1,1. So that's it. Thanks. So any question?
Any question from participant side? I think no.
Okay.
So
No
okay.
question.
Hello.
Yeah. You may ask. Yes. Yes, please. Abul, you may ask.
Okay, sir. In example of groups, example number 11.
Yes.
Go through the page. example of groups, example number 11.
Yes. Yes.
11, example number 9. Example number 9,
Yes.
5x equal to 1 has a solution x equal to 1 by 5. Can I write x equal to 1 by 5?
No, you can write inside the cube.
Inside the cube. But here Z star is the mother set. So I think we just say the equation 5x equal to 1 has no solution in Z star.
Yes, yes. So because if you can write 1 by 5 in Z star, then you have a solution. But you cannot get any solution in Z star, and that's why this 5 has no inverse, and that's why it is.
Okay, sir. Then my question is, can I write x equal to 1 by 5?
No, this is just for understanding. It is not better way is to write that this equation has no solution.
No solution in Z star.
This is just for simplification. Just I was trying to make a simplify. Just I was simplifying the whatever I.
If we consider Z star dot as a subgroup of Q star dot, then we can say x equal to 1 by 5, and that belongs to Q star but does not belongs to Z star.
Yes. So I was just saying that it has a solution but not in Z star. It has a solution in Q star.
Okay. Thank you, sir.
Any other queries?
Sir?
I think no. Yes. Yes.
There exists a homomorphism map between R and R star.
R and R star. I have given example just now. This exponential map is a homomorphism.
Sorry, it's from R to R plus, I think. I asked from R to R star.
Okay. You ask R to R star. So that is also in, I think, tutorial I have given or not. But yes, you can always get. Wait, yes. So your question is that R plus 2 R star. No? Hello?
Sir, R to R star.
Oh, here, yes. So here, this is a group homomorphism from R to R star.
Okay. Any other queries?
So this example one is actually map from R to R star. You are asking me this R plus and R star are isomorphic or not. I think your question is like that. Because this map is not onto. So you are expecting that some map from R plus to R star, which is onto.
1 and onto.
Yes. So basically your question is that is R is isomorphic to R star or not?
Yes.
Yes. So we'll take this in tutorial. Already I have given these questions, I think. So I will check, and I think in tutorial you will get answer.
Okay. Thank you, sir.
Any other queries? Okay. So I think no. So let us thank and clap for Dr. Singh for his very fundamental informative lecture. Yes, please. Okay.
So I have one suggestion, because most probably I'm going to do one game, and I like if you people can just search on Google something called a 15 puzzle game. 15 puzzle game. Game is like that. You have a 4x4 something square, and you have a number 1, 2, 3, 4 up to 15, and one place is open, blank. There is nothing is there. So you can move always your coins one side. So you just Google it, you will get a 15 puzzle game, and we are going to discuss in this lecture series. So it is my suggestion you people just go online and check what is a 15 puzzle game, and we'll discuss the proof of when you can solve or not. Such type of thing we will try to answer in this lecture series.
Okay, sir.
Because it will save our time. First time if I explain you, then it will take more time. So better you read, check it, and then we discuss.
Okay.
Okay, sir.
Thank you, Dr. Singh, for your suggestion. On behalf of all the participants and the whole organizing team, TW, I would like to thank Dr. Sanjay Singh for his nice and very explanatory lecture. We really amazed to see your way of explanation, which starts from daily life examples to the high, tough, pure mathematics of algebra. Once again, thank you so much, Dr. Singh.
Thank you.
We can just yes, sir. Yes, thank you.